Calculus is my favorite section in the whole of mathematics of 11th and 12th standard. Of course, the mathematics behind calculus is very exciting, but what makes calculus even more exciting is the fact that this section, just like me, is the favorite of all your examiners. Be it the JEE Main Exam or the Advanced Examination, a lot of questions appear from calculus. To be very honest, calculus has the maximum weightage among all the sections of mathematics of 11th and 12th standard in the JEE examinations. So we are going to start with calculus. We're going to take baby steps and we are going to look at limits today. Limits is the first and the most important chapter of calculus because this introduces you to the concept of calculus and sort of forms the foundation to calculus that is to follow. So what is the weightage that limits carry in the JEE examination? Well, generally, calculus carries about 25 to 30% of weightage in both your JEE main and advanced examinations. So in your main examinations, if you are supposed to have 30 questions, generally 8 questions, 9 questions, or sometimes 10 questions are from calculus. And 1 question is definitely from limits. I'm not talking about limits, continuity, differentiability. I'm just talking about limits. 1 question in the main examination is always from limits. This has happened from 2012 all the way up till the recently concluded 2019 JEE main examination. Every paper had 1 question where you had to evaluate a limit. So limits, a very, very important topic because 1 question comes from here. And what is more is that this question which comes is actually not a very difficult question. If you've done enough practice, if you understand the concepts of limits, this is a question that you can solve in less than a minute in the main examination, which means that you can allocate the rest of the time to some other complicated question. So limits is a short question plus an easy time-saving question. So please do not skip this chapter on limits if you're preparing for the JEE main examination. When it comes to advanced examination, of course, in the past 4 years, we've seen 1 question come from limits wherein you had to evaluate the value of a limit. But these questions are not as simple and trivial as the questions that come in the main examination. These questions will have certain convoluted tricks which will make this question a little difficult to solve. In fact, the question which came in the year 2014 was one such question wherein you had to evaluate the value of a constant which was there in the expression of a limit. They'd given the value of the limit, you had to evaluate a limit and find out the value of a constant, and that was a very, very tricky question. So sometimes in the advanced examination, the questions from limits tends to be tricky, but there are only so many concepts which are there in limits. So, in case you have gone through the entire syllabus, done enough practice, the examiner actually cannot surprise you in the question paper. So limits is a chapter that you must thoroughly go through and make sure that you do not go wrong in that 1 question which comes in the main examination and 1 question which comes in the advanced examination. True that the advanced exam question might be a little tricky, but why are we here for? We are here to make sure that you know the tricks of the trade. Since limits is the first unit of calculus, we begin by looking at the fundamentals. We start by looking at what the definition of limits is. So we look at what the definition of limits is, and then we move on to the very important concept of existence of limits. Now, when does a limit exist? What is the meaning of left-hand limit? What is the meaning of right-hand limit? And what relevance do these terms hold in the context of existence of limits? Because if you understand this, your foundation of limits has been laid. And over this, we build a lot of other concepts such as algebra of limits. And finally, we move on to the most important part of limits, which is the indeterminate form. There are 7 different indeterminate forms, and in fact, all of these different indeterminate forms are more or less the same thing. They all can be interconnected from one form to another. And remember, indeterminate form fetches questions in almost every examination. This is the single most important concept in the chapter of limits. How to evaluate the indeterminate form forms the crux of this chapter on limits. And for that, we have a number of theorems. The most important theorem is not the sandwich theorem, but the L'Hopital's theorem. Now, L'Hopital's theorem is something that Generally, your 11th and 12th standard teachers don't like teaching because this is sort of a shortcut theorem. But that's the most important theorem when it comes to competitive examinations, because your steps are not important. You have to arrive at the final answer, and somehow L'Hopital's theorem works wonders and helps you arrive at the answers pretty easily. Speaking about the sandwich theorem, well, this is more of a mathematical theorem which is used to prove things. This does not find a lot of application in your JEE Main or Advanced examination. The most important theorem is the L'Hopital's theorem. Evaluating the limits, the most important concept. L'Hopital's theorem, the single most important theorem from this chapter on limits. After mastering the concepts of limits, we slowly build on to the concept of continuity. So continuity is just an extension of limits. We speak about the right hand limit and the left hand limit, and then we speak about the value of the function at the point. If the right hand limit is equal to the left hand limit, we say that the limit exists. And if these two limit values equal to the value of the function at that point, we say that the function is continuous. So that's all about continuity. There isn't much more to continuity than this very simple concept. Of course, when we talk about continuity, we do speak about discontinuity. So there are two different types of discontinuities, and we discuss these different types of discontinuities. And more often than not, when a question comes from the concept of continuity, the concept that is tested is discontinuity. So it's important for you to understand discontinuity. Speaking of limits and continuity, what is really important is for you to visualize these concepts. You have to understand what a left-hand limit means graphically, what a right-hand limit means graphically, what continuity means graphically. And to be very honest, these are very simple concepts on a graph. If you can draw a graph without lifting a pen, it means that your function is actually a continuous function, right? Then we move on to the last concept of this chapter, which builds on to the rest of calculus, which is differentiability. Now, what is differentiability? Differentiability actually is nothing but the slope of a tangent drawn to a curve at a point. Now, if a function is differentiable, then that means that at any given point, you have a unique tangent to the curve. If the function is not differentiable at that point, it means that you can draw multiple tangents to the curve at that point. One prerequisite for any function to be differentiable is that it should be continuous. But if a function is continuous, it does not mean that the function is differentiable. So if a function is differentiable, in the graphical sense, it means that the function does not have any sharp edges, which means that the modulus function is not a differentiable function because very evidently it has a sharp edge, and at that point, the value of the slope takes two different values on either side of the sharp edge. So this is all about limits, continuity, and differentiability. We look at when limits exist, when a function is continuous, and when a function is differentiable. But there is much more nitty-gritty details in this chapter, and these nitty-gritty details will help you solve questions. I'm going to very quickly take you through some interesting questions which will ease your preparation for the JEE Main and Advanced examinations. So let's quickly have a look at some questions and explore the beauty of limits, continuity, and differentiability. In this question, we've been asked to evaluate the limit that is given. Limit as x tends to 0 of a summation. Now the summation is r from 1 to 100 of the greatest integer of x raised to r. That is all divided by 1 plus modulus of x. So we have to evaluate this limit. Now this seems to be a little difficult to evaluate. So what we're going to do is we're going to make use of the basic principles of limits. We're going to compute the left-hand limit and then compute the right-hand limit and then find out if these two things match. If they match, then whatever that value is, that is going to be the value of the limit as x tends to 0 of this function. Fine. So what is the left-hand limit? Limit as x tends to 0 minus. This means that x is a very small number which is slightly less than 0. It's a negative number slightly less than 0. Okay, so now x tends to 0 minus of, I'm going to expand the summation and write it as greatest integer of x plus greatest integer of x square plus greatest integer of x cube all the way till greatest integer of x per 100 divided by, now I have 1 plus mod x in the denominator. X is a negative number, so if x is a negative number, mod x will be minus x, so I have 1 minus x in the denominator. So this is what happens to the denominator. So this is what I have to evaluate. Now let's try and see if we can evaluate this limit. So x is a negative number, slightly less than 0. So what is the greatest integer of x? A number which is slightly less than 0. That's equal to -1, isn't it? Now if I square that number, it's going to be still a small number between 0 and 1, because the square of any number between 0 and -1 is going to be a number between 0 and 1, and the greatest integer of a number between 0 and 1 is equal to 0. Similarly, x cube would be a negative number between 0 and -1. So this is going to be greatest integer of that is going to be -1. If I take an x power 4, I'll get the greatest integer of that to be equal to 0, and so on. I see that every odd number will give me a -1, and every even number, either power of x, is going to give me a 0. So I have how many zeros and how many ones? In fact, I have 50 zeros and 51. So the numerator is going to add up to 50, and with the negative sign is going to be -50. The denominator, of course, when evaluated, is going to give me 1 minus 0, which is equal to 1 itself. So the value of the left hand limit is -50, because there are 50 minus 1s in the numerator. Now let's look at what happens to the right hand limit. In the right hand limit, so that is going to be limit x tending to 0 plus. This means x is a very small number, very close to 0, but it's a positive number. Okay, so now the greatest integer of x, well, the greatest integer of x is going to be equal to 0, because it's a small number, slightly more than 0. X square is also going to be a smaller number, slightly more than 0. That's going to be again 0, and so on all the way up to 100. I'm going to get lots and lots of zeros, and the denominator now is going to be 1 plus x, not 1 minus x. I'll have a 1 plus x in the denominator. The reason being, x is a positive number, so the modulus of x is going to be positive. So I have 1 plus x in the denominator. Doesn't matter if it's a minus or plus, because I eventually have a 1 plus 0, which is going to give me a 1 itself. So the value of the right hand limit is going to be equal to 0. The left hand limit is -50, the right hand limit is 0. This means that the limit does not exist. So the correct answer to this question is that limit does not exist. So sometimes in limit questions, we cannot make use of any tricks that we know to solve limits. We just have to go to our basics, stick with the basics, and solve a question using the first principles, which is compute the left hand limit, compute the right hand limit, see if they are equal or not. If they are equal, that's the value of the limit. If they are not equal, then the limit does not exist. This is how you solve a limit question sometimes. And such questions appear more often than not in the advanced examination, because tricks are not what advanced examinations check for. They check for your conceptual clarity, and this question actually checks your conceptual clarity. Now let's look at yet another question, this time a question wherein the limit tends to infinity. So in this question, we have to evaluate the value of limit x tending to infinity of this particular expression. So whenever you see a problem that has a limit which goes to infinity, you should try and bring that variable in the denominator. Because if that variable is in the denominator, then anything divided by infinity will give me a 0. If a finite number is being divided by infinity, then I'll get a 0 very easily, and then I can evaluate limits pretty simple. Now let's look at what is there in this expression. I have 5 to the power sine x. We know what happens to sine x. Sine x is always going to lie between -1 and +1. Even if you put the value of x as a huge number, extremely big number, it is still going to lie between -1 and +1. So 5 to the power sine x is always going to lie between 5 to the power -1 and 5 to the power 1. So this means that 5 to the power sine x is going to be a finite quantity even if my x is infinite. But 2x, the next term, that's not going to behave in this way, because 2x is going to grow linearly as x grows. If x becomes infinite, 2x also becomes infinite. 1 is definitely a constant. So what will happen if I divide this by x? Now 5 to the power sine x is finite, divided by x will give me a finite divided by infinite 0. 2x divided by x, the x's will cancel out and I'll be left with 2. That's finite. 1 by x, again, 1 is a finite quantity, a constant rather, divided by infinity is going to go to 0. So if I divide the numerator by x, I can more or less handle the limit. But what about the denominator? Now the denominator here, I have a cos x. The cos x is again going to behave exactly like sin x. Irrespective of what value of x you put, this is going to lie between -1 and +1. So cos x is going to be a finite value. So if I divide that by infinity, I will get a 0. What happened to root of 1 plus x square? Now root of 1 plus x square is also going to grow exponentially as your x grows. In fact, it's going to go in a quadratic way as my x grows. So if I divide this also by x, because if I divide the numerator by x, I have to divide the denominator by x, cos x will be taken care of. Let's see if under root of 1 plus x square will be taken care of. So I can rewrite the entire limit in this way. Now let's look at what happens. So 5x by x as s goes to infinity, this goes to 0. This also goes to 0. 2 is going to stay as 2. So my numerator is going to be 2. Let's see what happens to the denominator. Cos x by x, that will go to 0. And under root of 1 plus x square plus 1. Beautiful. Because this term here goes to 0 and 1 is going to stay as 1. So that's going to be negative of the square root of 1, which is 1. So I will be left with 2 by -1. So the value of this limit is -2. A very interesting question. I like this question a lot because this is a beautiful question. In fact, if you look at the limit here, the limit would have been a something of the form infinity by infinity, which you could have solved using the L'Hospital's or the L'Hopital's theorem. But look at the kind of functions which are there. Differentiating these functions would have been difficult. So this was the best and the easiest way of solving this question. This question is not a very difficult question, definitely not an advanced level question, but such questions do appear in your main examination, and this is the trick that you will use to solve this question and not L'Hopital's. We generally have this misconception that as soon as you see a limit question, the first thing that you try to do is solve it using L'Hopital. If that doesn't work, that is when we come back to the conventional methods. No, because time is very crucial in the main examination, and this question, if you would have done it using L'Hopital's, you would have had to differentiate 5 to the power sine x under root of 1 plus x square. Not necessary. So we're going to use this conventional method of solving a limit as x tends to infinity and solve this question in real quick time. Now that I spoke about L'Hospital's or the L'Hopital's theorem so much in the previous question, let's do a question which is extensively based on the L'Hopital's theorem. So in this question, we've been given that the value of limit as x tends to 0 of f of x divided by x is 10. And then the limit as x tends to 0 of f of sine x divided by g of x cos square x is 5. They further told us that g of 0 is 0 and asked us to evaluate the value of this limit. So let's try and analyze what are the things that are given to us. F of x by x as limit x tends to 0 is equal to 10. Now if I substitute the value of x in this limit, x is equal to 0 in the denominator, I get f of 0 divided by 0 equal to 10 and not an infinite value. So f of 0 divided by 0 is not an infinite value but 10. This means that f of 0 by 0 should have been an indeterminate form, and it's actually a 0 by 0 indeterminate form that I'm looking at. And so I'm going to solve it using L'Hopital's theorem. So that can be rewritten as limit of x tends to 0 of f dash of x divided by 1, and this we know is equal to 10. So that means f dash of 0 is 10. Correct? So I have got f dash of 0 to be equal to 10. So this is one piece of information that I am going to keep. Next, let's make use of the second condition, limit x tends to 0 of f of sine x divided by g of x cos square x. Now sine x is 0 as x goes to 0, so that this would be f of 0. Then g of x, we know g of 0 is 0, so this is 0. Cos square 0 is 1. So I actually have a 0 in the denominator. Again, this limit is not an infinite value but a finite value. This means that my limit is again an indeterminate form. So I am going to use the L'Hopital's theorem again, and this can be rewritten as limit x tends to 0 of f dash of sine x, and then remember to use the chain rule of differentiation. So that's going to be multiplied by cos x, and then you have to divide this entire thing. Now you're going to make use of the product rule of differentiation. You're going to get g dash of x into cos square x plus g of x into 2 cos x, again chain rule, into minus sin x, and this is all equal to 5. Now let's try and evaluate cos of 0. This term is equal to 1 here. Sin x is going to be 0, so I have an f dash of 0 in the numerator, divided by g dash of 0 into cos square x is again equal to 1. Now g of x, that's equal to 0. So I actually have f dash of 0 divided by g dash of 0 equal to 5. What was f dash of 0? F dash of 0 was 10. So g dash of 0 is 10 by 5, which is equal to 2. So I have got my second interesting observation from the two given conditions. F dash of 0 was 10, g dash of 0 was 2. Now let's try and evaluate the limit which was at hand. The limit x tends to 0 of g of 1 minus cos x divided by x square. Immediately cos x as x goes to 0 is 1. So I have g of 0 divided by 0. Correct? So I have a g of 0 divided by 0, and this I'm going to evaluate again using the L'Hopital's theorem because g of 0 was 0. So I have another indeterminate form of 0 by 0. I'm going to make use of the L'Hopital's theorem for the third time in this question. So I get limit x tends to 0 of g dash of 1 minus cos x, and don't forget the chain rule of differentiation, multiplied by the differential of 1 minus cos x, which turns out to be sin x, and this divided by 2x. So limit x tends to 0 of sin x divided by x equal to 1. So I have g dash of 1 minus cos 0, which is 1. So 1 minus 1, 0. So I have g dash of 0 divided by 2. So what is g dash of 0? G dash of 0 was 2. 2 divided by 2 is equal to 1. So the correct answer to this question is 1. So this question was an extensive application of L'Hopital's theorem. Now this was not a very straightforward application of L'Hopital's theorem because in the given condition, you had to visualize that actually the limits were indeterminate forms. These were not given to us. That comes from experience and practicing a lot of questions which had something to do with L'Hopital's theorem. From there, we got to know that there were indeterminate forms, and using those conditions, we arrived at some relations and used that relation to finally solve the question which was handed. Very, very, very interesting question. And of course, L'Hopital's theorem is our favorite when it comes to limits. So this question was a very interesting question. So in this question, we have to find out what is the value of limit as n tends to infinity of this expression which is given to us. So how do you go about a problem which has a limit of a variable tending to infinity? One way to do that is to bring that variable in the denominator. Now, is that possible in this question? Well, not really, because what you see is you have all the n's in the exponent here. So when the n's are in the exponent, we cannot bring it down in the denominator. So then what is the trick that we use when we have a variable tending to infinity? Then the trick that we use is to make sure that the number which is raised to that variable, which is going to infinity, is less than 1. Because any number which is less than 1, which is between 0 and 1, when raised to infinity goes to 0, correct? So that is what I'm going to do here. So first thing I'm going to do is I'm going to rewrite my expression as limit n tending to infinity. So I want to keep just 5 to the power n's and 3 to the power n's. So all these raised to the power n plus 1, I'm going to convert them and write them as 25 to the power n minus 2 into 3 to the power n. That's not going to change. Divided by, now 3 to the power n plus 1 is 3 times 3 to the power n. So that's going to be 18 3 to the power n plus 5 to the power n. So that's how I'm going to rewrite this. Now what I will do is I will divide both the numerator and the denominator by 5 to the power n. As soon as I do that, my expression is going to change into this particular form here. So I will have a 20, then I'll have minus 2 and 3 by 5 to the power n. Similarly, the denominator changes to 18 into 3 by 5 to the power n plus a 1. Now I'm going to apply my limit. What happens as soon as I apply my limit? So this term here, this goes to 0 as n goes to infinity. This term also goes to 0 as n goes to infinity. This means that I am left with just 20 in the numerator, 1 in the denominator, which means the answer to this question is just 20. A very simple question wherein you have a limit as n tends to infinity. This is another variant of n tending to infinity. In fact, this question could have been solved in a different way. This question would have had an infinity by infinity form. You could have used L'Hopital's, but that would have made the question extremely cumbersome, and we're not sure if we would have actually got the answer. This was a very easy method of arriving at the solution. In this question, we've been given that alpha and beta are the two roots of the quadratic equation ax squared plus bx plus c equal to 0. So this is the quadratic equation we have. Alpha and beta are the two roots of that equation. The objective is to find the value of this limit here. So the limit has x tending to alpha, and then in the numerator you have 1 minus cos of ax squared plus bx plus c. So the polynomial ax squared plus bx plus c, this polynomial is the argument of cos. This is all divided by x minus alpha the whole square. So what happens when you put alpha for x? Well, if you substitute alpha for x, you get cos of a alpha square plus b alpha plus c, and a alpha square plus b alpha plus c is actually equal to 0 because alpha is one of the roots of the quadratic equation ax square plus bx plus c equal to 0. So you actually get 1 minus cos 0 divided by alpha minus alpha is 0, so that is 0. 0 square is 0. So cos 0 is 1, so you actually get a 0 by 0 indeterminate form. You can well use the L'Hopital's theorem, differentiate and arrive at the solution. But then if you actually look at the L'Hopital's way of doing it, if you differentiate once, you will get a 2 times x minus alpha in the denominator, which means that you are going to again end up with a 0 by 0 form, and you might have to differentiate a second time. I am not a big fan of differentiating so many times, so I'm actually going to tell you the correct method of solving this question without a shortcut, which happens to be the shorter method to solve this question. Let's analyze the quadratic we have in our hand. Ax squared plus bx plus c equal to 0 is the quadratic equation with alpha and beta as its roots. This means that I can factorize ax squared plus bx plus c in terms of alpha and beta, right? So I can write ax squared plus bx plus c as x minus alpha into x minus beta. Is that all? Am I right? There's a small twist here which many students forget, and because of which they go wrong in the solution to this question. Ax squared plus bx plus c is not equal to x minus alpha into x minus beta, but it is equal to a times x minus alpha into x minus beta. That a is very crucial, and you cannot forget that a. Now, as soon as you write in the a there and factorize ax squared plus bx plus c in this way, now I am going to rewrite my limit in this particular way. So I'm going to write the argument ax squared plus bx plus c in cos as cos of a times x minus alpha times x minus beta. I don't change anything else as of now. Now, what is 1 minus cos theta? 1 minus cos theta is nothing but 2 sine square theta by 2. I'm going to use this form because I like limits with signs in them, because if sign is there in the limit, I know that limit as x tends to something, sine theta divided by theta goes to 1. So I'm going to use this form. I like the sign there, so I'm going to use that form. So now I have limit as x tends to alpha of 2 sine square of the whole thing, a times x minus alpha into x minus beta divided by 2. The argument gets divided by 2, all divided by x minus alpha the whole square. Now, if I consider a change of variable, if I consider a x minus alpha into x minus beta divided by 2 as my new variable with the limit, and all this going to 0, because if x goes to alpha, a times x minus alpha times x minus beta divided by 2 goes to 0, right? So then that is going to be my new variable. If I consider that, then I can somehow bring in the sine theta by theta form. So what do I have to do? I have to divide, because there's a sine square, I have to divide by a square, because it's a times x minus alpha into x minus beta by 2. Then again divide by x minus beta the whole square and divide by 2 square. So if I divide by all these things, I also have to multiply by all these things. So I multiply by a square x minus beta the whole square divided by 4. Now, if my variable was a x minus alpha x minus beta divided by 2, and we know that goes to 0 because x goes to alpha. So if that was my variable, then this entire expression here, this expression here goes to 1. When that variable goes to 0, this entire expression goes to 1. So as x goes to alpha, this entire expression goes to 1. Which means that I am just left with 2 times a square x minus beta the whole square by 4. The 2's and the 4's can cancel out, and then I plug in the value of x as alpha. So the final answer to this question is just a square alpha minus beta the whole square divided by 2. So a very, very nice way of solving this question without using the L'Hopital's theorem, and turns out this is much easier than using the L'Hopital's theorem. Now the trick to this question was very simple. You have to factorize ax square plus bx plus c as a times x minus alpha times x minus beta, when alpha and beta are the 2 roots of that quadratic equation. If you forget the a, you will end up with a disastrous solution. So make sure that you pay attention to details. Now, this is an application of quadratic equations in the chapter of limits. So this is how important quadratic equations is. Of course, limits is also a very important chapter. A very interesting question, merging concepts from 2 very interesting chapters. Let's move on from limits to continuity and differentiability. Let's quickly have a look at one question from continuity and differentiability. So in this question, we have been given the definition of a function. And we see that this function changes definition at 2 points, at x is equal to 0 and at x is equal to 2. Less than 0, there's a definition. Between 0 and 2, there is a definition. And after 2, there is yet another definition. So if you look at the way this function is, less than 0, the function is actually a quadratic function. Between 0 and 2, it's an exponential function. And in fact, after 2, this function is actually a linear function. So it's a very interesting function. And the objective of this question is to find out the points at which mod of f of x is discontinuous, and also the points at which mod of f of x is not differentiable. So it's a multiple correct answer kind of question. So again, remember there are partial marks for each correct answer. So you might stop at the continuity itself if you don't want to go ahead and look at differentiability. So the 2 options speak about continuity, 2 options speak about differentiability. So you can stop at continuity if you don't want to go ahead. But of course, we always try and solve the entire question and get all the marks that are on offer from the question. But I'm going to solve this question in a way in which you cannot skip the part of differentiability, because I'm not going to solve this question algebraically or using the concepts of calculus on paper using algebra. What I'm going to do is I'm going to solve this question graphically, because graphically we can very easily visualize what happens to a continuous or a discontinuous function and a differentiable or a not differentiable function. So I'm going to plot the graph of this function. So this is what happens to the function before x equal to 0. So in the entire domain which is x less than 0, it's a quadratic function x squared plus 2. So at x is equal to 0, which is just less than x is equal to 0, the function is going to be very, very close to 2. Between 0 and 2, now this is an exponential function. So what happens when you put in the value of x is equal to 0? When you put in the value of x is equal to 0, the value of the function is going to be negative 2. So you see the function itself is not continuous at x is equal to 0. So it's going to start from -2, and as you go on increasing the value of x, the value of the function is going to slightly increase. So at x is equal to 2, the value of the function is going to be -2 divided by e square. Now this is a value between 0 and -1. So it's going to be an exponential curve, which is basically going to increase from -2 to -2 by e square. What happens after 2? So after 2, the function is going to be linear, but the slope of this function is going to be -2 divided by e square. Wow, that's an interesting number, right? Because the value of the function at the point 2 was -2 over e square. So at the point x is equal to 2, the value of the function is going to be +2 over e square, because you have x minus 3 there. If you plug in the value of x equal to 2, this is what happens. So the value of the function is going to be +2 over e square, and the function basically decreases from then on, and it goes down into the negative quadrant, into the fourth quadrant basically. So this is how f of x behaves. Look at f of x. F of x is clearly not continuous at 2 points x is equal to 0 and x equal to 2. But that's not the objective of the question. The objective of the question is to find out where the function mod of f of x is continuous or not. Now, how do you find out the graph of mod of a function? Whatever is in the negative axis, just reflect it about the x-axis. So you're going to consider the x-axis and reflect whatever is below it above it. Now look at the graph of the function. Wow, it's a very, very interesting question, because now this function is not discontinuous anymore, because at x is equal to 0, both on the left hand side and the right hand side, the value of the function is very close to 2. At x is equal to 2, the value of the function is very close to 2 over e square. A very beautifully designed question, isn't it? So the function is in fact discontinuous at 0 points. The function is continuous everywhere. Moving on to differentiability, let's analyze the points where the function may or may not be differentiable. Before x equal to 0, that is to the left of x equal to 0, everywhere this function is definitely differentiable because the function is a quadratic function. But at x equal to 0, the function definition changes. From quadratic, it becomes an exponential function. So this is a point that we need to be a little careful with. Then there is x equal to 2. At x equal to 2, the function changes from exponential to linear. So this is also a point where we have to be a little careful about checking whether the function is differentiable or not. Now, are these the only 2 points we have to be careful about? Hang on. Because we are considering mod of f of x, there is one more point which becomes very crucial. That is the point where the linear curve changes direction. The linear function that we have changes direction at x equal to 3, and we clearly know that at this point the function is not differentiable. So we already have one point where the function is definitely not differentiable, that is x equal to 3. So we might have 2 more points. Let's see what happens at x equal to 0. Before x equal to 0, the function is a quadratic square plus 2. Mod doesn't actually change the function definition of this. So mod of f of x is also going to be x square plus 2. So if you differentiate this, you get 2x. And at x equal to a value which is very close to 0, the slope of this function is going to be almost equal to 0. Now what happens on the right? On the right of x equal to 0, it's an exponential function, -2 e to the power negative x. But when you take the mod of the function becomes 2 e to the power negative x. So what is the differential of this? The differential of this is nothing but -2 e raised to negative x, and at x is equal to 0, the slope is not equal to 0, but the slope is equal to -2. So on the right of x is equal to 0 and on the left of x is equal to 0, we have 2 different slopes, which means that there is no unique tangent, which means the function is not differentiable there. Now let's look at x equal to 2. Left of this, it's an exponential function. We have differentiated it, -2 e raised to -x. So at x equal to 2, on the left side, the value of the slope is -2 divided by e square. What happens in the right side? Now in the right side, it's a linear function, negative 2 over e square x minus 3. When you differentiate it, the slope of this linear function is also negative 2 over e square. Look at the beauty of this question. At x equal to 2, even though the curve changes definition from an exponential to a linear, there is a unique tangent there. So at x equal to 2, the function is actually differentiable. So there are only 2 points where this function is not differentiable, x equal to 0 and x equal to 3. X equal to 2 in fact is a point where the function is differentiable. So the correct answer to this question is that the function is discontinuous at 0 points and is not differentiable at 2 points. So these are the 2 correct answers to this multiple correct answer question. A very intelligent question, and you have to be very careful before you conclude things with this question. I hope you had fun solving this question. We'll solve yet another question. After that very interesting question, let's look at a slightly easier question from the concepts of differentiability and continuity. This is the question. So in this question, we've been given a function f of x with this definition of the function. So the function definition changes at x is equal to 0. And they've told us that the function f of x is differentiable at x is equal to 0. The objective is to find out the value of this expression, which is the modulus of a plus the under root of b square minus 1, which means that we have to find out what the values of a and b are. You can find a and b in the function definition. So we are just going to make use of the data that is given and arrive at the values of a and b, plug them in the expression that we need to find out, whose value we need to find out, and that's how we arrive at the solution. So the first thing, they've told us that the function is differentiable at x is equal to 0. So since it has been told that the function is differentiable there, it means that the left-hand derivative and the right-hand derivative is going to be exactly the same. So if the left-hand derivative and the right-hand derivative are exactly equal, let's compute the value of the left-hand derivative and the right-hand derivative. Now, it's an advanced examination, so we are not going to make use of the first principles. We are going to just differentiate whichever function has been given. So on the left-hand side, I have to differentiate this function a e to the power minus ax, and I know what its derivative is. Its derivative is simply a into negative a times e to the power minus ax, which means I get a negative a square e to the power negative ax, evaluated at x is equal to 0. So at x is equal to 0, I'm going to get the value as negative a square. Very simple. Now I differentiate the right side of this function. So on the right side of a, the value of the function is going to be x cubed minus 4x plus 2b. I just have to differentiate it. It's a polynomial, very easy to differentiate. So I get 3x square minus 4 evaluated at x is equal to 0, and the value turns out to be equal to negative 4. Since the function is differentiable at x is equal to 0, this means that the left-hand derivative and the right-hand derivative have to be the same, because at x is equal to 0, we have to have a common tangent. So this means that negative a square should be equal to negative 4, or a square equal to 4. If a square equal to 4, mod a is going to be equal to 2, because I need the value of mod a. I am not going to consider a to be equal to plus or minus 2. Mod a equal to 2. So I have found out the value of mod a. Now I need to find out the value of b. What other details do I know? I have made use of everything that has been told, hasn't it? In fact, there is an implied information which I have not made use of. They've told us that the function is differentiable, which implies that the function is continuous at that point. So if the function is continuous, then the limit exists at that point. So I'm going to make use of the limit. Let me compute what is the left-hand side limit. So the left-hand side limit is going to be limit as x tends to 0 minus of the function, which is going to be a times e to the power negative ax. That has to be equal to the right-hand side limit, which is limit as x goes to 0 plus of that polynomial x cubed minus 4x plus 2b. So now if I plug in the value of x is equal to 0 here and here and here, what do I get? I get a equal to 2b. So if a equal to 2b, well, b can be equal to plus or minus 4, right? Because a is equal to plus or minus 2. But what are we interested in? We are interested in finding the value of b square. So let's just square this equation. So that implies a square equal to 4b square. So if a square equal to 4b square, b square equal to a square by 4, a square was 4, which means b square was equal to 1. So mod a is 2, b square is 1. So the value of the expression is 2 plus under root of 1 minus 1, which is equal to 2. A relatively simple question, but the only trick was there was an implied piece of information which we had to make use of. We were given that the function is differentiable. We had to imply that the function was continuous and hence limit existed at that point, and just make use of that piece of information and solve this question. A relatively simpler question than the one which we solved previously. So limits, continuity, differentiability is an important chapter, forms the basis of calculus. More importantly, a short chapter for questions in both your main and advanced examination. What's more important is the questions are not very difficult. These are questions that you can actually very easily solve in a double quick time. So you actually don't need the amount of time that you allocate per question to solve the limits question, which means you have some free time at your hand after solving the limits, continuity, differentiability question, and this time you will use to solve the extra lengthy questions. Make sure you practice limits, continuity and differentiability very well and score all the marks that are on offer from the questions that come from this chapter. Have a happy time studying, and I will see you very soon with another new video.
For more videos and live lectures on the JEE, click on the subscribe button now.